previous lecture, I was discussing about self-supervised learning. The main goal of self-supervised learning was that we often do not have a lot of data for a new task at hand. So we can use things like paradigms like transfer learning. Self-supervised learning has been very popular in the recent few years, where the idea is that we can create some transformations of the input data and we know the labels for those transformations. Right? So we took a few examples. We took images and we rotated them by 0, 90, 180 and 270 degrees. And our task was, can you tell by how much this particular image has been rotated? Now, by doing such things, what we're hoping is that we can learn some useful representations from the self-supervised task without giving explicit supervision. With explicit supervision would be, let's say, a classification task. We call all of these as downstream tasks: classification, segmentation, etc., localization. But instead of that, in self-supervised tasks, we have given the self-supervised labels, right? But we're hoping to be able to learn some structure, some useful structure from this self-supervised task, which when then fed through to the downstream task, we can very quickly fine-tune and get something useful. Today, we are going to be looking at another setup, which is active learning, right? So in the previous setup, if you remember, we had our input, our total amount of data, which was broken down into training data, testing data, and everything else was called pool data. For the previous task, we assume that pool data, we know the input features, right? But we don't know the output label. So think of this as anything that you can get freely on the internet is a pool, is an instance of what may go in the pool data set, right? Which would require you some effort to label. But if you were to just acquire inputs, they are almost free, right? So today we'll be looking into active learning, and we'll say that which of these pool points should we be labeling in order to improve the model accuracy the most. Previous class, self-supervised learning, we were not labeling pool examples. We said that let's give these pool examples to a self-supervised task. Pre-task, pre-training, all of these terms are often used synonymously. But today we will be trying to get the actual labels. Right? Why don't we get labels for all the possible examples that we can get? So if we have the mechanism to get labels, why don't we go ahead and get the labels for all the pool points? It is tiresome. You will have to have some amount of expertise in order to label certain images or audio files, etc. Right? So supervised learning has really taken off in the past few years, and we know that it's primarily three things. One, massive amount of data which has now become available. So I talked about this briefly in the previous lecture also. Before ImageNet, a lot of the computer vision research was using classical methods and was working only on 1 to 500 images, very small number of images. Whereas with the ImageNet, people started looking into much larger data sets. So which enabled much better models to be trained. So in the whole pipeline formed. Second was better algorithms. As an example, better activation functions, better optimization routines, better ways of initializing networks, better ways of pruning networks, better ways of regularizing networks. All these are improvements to the algorithms. The third is better computational infrastructure, which means better GPUs, more efficient algorithms, more efficient systems. Right? So all of them were playing together. But still, most of the research at this point of time was looking into supervised learning, which assumes access to labeled data, which is very expensive. Right? So let's consider some examples. So let's consider this specific task. This article is what Zeal and I wrote 2-3 years back. So this is a speech. Okay, you can't hear it. But in this particular speech, Zeal was saying something, hello, this is an article on active learning. Right? Now, to you, this may be very simple of just task of just recognizing it. But imagine if you have to create a labeled data set for this, where you have to tell which phonetic was spoken at each millisecond. Right? So you'll have to get a time series of this audio signal. You'll have to segment that across various smaller time windows. And then for each of them, you have to tell whether A was spoken, I was spoken, what exactly was being spoken, right? So this was how a lot of classic speech processing was being done using models like hidden Markov models. Now, of course, a lot of this goes into deep learning pipelines, right? Either you create a spectrogram or you just pass it to some 1D CNNs or models like LSTM, etc. And you can think of this as a sequence to point kind of a task, right? But if you were to manually create a lot of features, it would not be very easy. Or if the task is just speech to text, when you have to create the labels, and the label being for a very specific time window, what was the phonetic being spoken, it is not an easy task to annotate, right? For this 6-second audio, it may require a minute, it may require an hour, depending on the task at hand, right? Let's look at another task, human activity recognition. So let's say if a person is walking, running, sitting, climbing, you want to tell that based on a machine learning approach. So firstly, can you tell me what kind of a sensing system might you be using? Okay, now not the first S. Last seat. What kind of a sensor might you use to detect human activity? Okay, accelerometer, who said that? Okay, accelerometer. So accelerometer will give you time series readings. Based on that time series reading, you will say that perhaps when you're running, the accelerometer will show more deviations. When you're sitting, more or less certain, and gravity pointing out in certain directions. Climbing, you will have a rhythmic pattern, right? So you could use accelerometer. That is one kind of sensor. Ritik? So accelerometer, gyroscope, you'll typically consider them as a part of IMU. Camera. So you can have computer vision based methods. What else? Sorry? Thermal imaging, which is again a camera, but a thermal camera. Okay, that side. Anyone? Heart rate. Okay. So heart rate would be increased when running. It would be slow when sitting, and climbing. It will maybe show some rhythmic patterns. Any other sensor? Sorry? Breathing pattern. What kind of a sensor would you use for that? Blood oxygen levels or the amount of respiration rate. Although respiration rate might be a more involved signal, like heart rate may be a more direct signal. Actually, even heart rate is not a very direct signal. You measure something else which that gets converted into the proxy for heart rate, and then you can use that further. Similarly, for respiration, you will not be able to very easily measure respiration directly. You'll measure something else through which you will get respiration. Motion capture, I'm assuming, is computer vision, so or something similar, or let's say some laser, lidar, radar based systems. EMG based systems. So you instrument the person with dozens of sensors. Torque sensor, okay. But eventually, when you've done all of this, you would still have to have a human being look at the person's activity and tell between what microsecond was the person walking, running, sitting, climbing, right? So typically, what the way this is done in the field is that you will give them a script. You'll give the participants a script between this second to the second, and you can have someone will have to have a timer and tell them now it's time to stand up, now it's time to run, now it's time to sit, climb, etc. What could be the issue with that? They may not adhere to it, they may not be synchronized perfectly, which again makes the task of the person who is labeling very hard. Typically, it's a human who labels the values, or there is a much more refined standard called the gold standard, right? Which is also very likely to be a sensor system, but it's something which is very well accepted in the community. So you can't be using your own sensor to act as a ground truth for what you're trying to predict. Right? You typically won't do that. You can use a commercial system or a very well established gold standard system as the ground truth. So I hope at this point I've convinced you that labeling points is very hard. Therefore, supervised learning is very hard. So in fact, in a lot of the experiments, a lot of the studies which we have done in our lab, so let me give you an example. In one such system, we were using a mask-based system to tell about your lung health indices. If you've not, So it typically takes about 2 hours of experimentation to get a quality data sample, right, of a lot of researcher time. So that's why getting quality ground truth is incredibly hard. So our study in that case had about 50 samples. Now in the modern computer systems, machine learning systems, you may think of 50 being useless number, right? 50 is a very, very small number. Even Iris dataset has 150 samples, right? So, but in practical scenarios, getting such samples is incredibly hard. And that is why we are studying topics like active learning. And another interesting thing about active learning, or the motivation behind that, is that all the samples may not be equal, right? There could be some samples whose labels, even if you get, you will not add much to the model, right? So remember, the broader aim being you want to improve the model the most in as few samples as possible, as few labeled samples as possible, right? If I tell you samples which give you no information at all, then those samples are probably not very useful to add, right? Let's take an example. I'm showing you 4 potential points, A, B, C, D, whose labels we don't know at this point. Which of them do you think is not a very useful point to get a label for? Who says A? Who says C? Who says B or D? Not very useful was the question. Okay, anyone who's saying C? Yeah, why do you think?
It's easy to recognize and inspire, so it doesn't add information how to classify it.
Yeah, so your aim was to make the model better. In SVMs, you know that everything on one side of the boundary would be treated as one class and the other will be treated as the other class. Now you can keep adding points here, but does that change your classification boundary? No. Or very mildly it may change just because of slack conditions, etc. But more or less it will not change the boundary. But for B and D, one, they're very close to the classification boundary. And there's signs also you need to see, you'll have to carefully see. For example, for D, it is occurring on the other side of the boundary. So you'll have to account for the slack for this. And this will then very likely change the decision boundary, right? So through this, we get to understand that not all the points will be equally useful to get labels for, right? Which means that so previously our question was in active learning was, can you find out the points which are which improve the model's performance the quickest? But now what we are saying is that, can you figure out those points which add the maximum value to the model, or about which the model may be most uncertain about, which will change the model the most, right? These are various kinds of definitions of what makes a good point to be labeled, good to be labeled, sorry. So for now, we'll be looking at a very simple MNIST classification task. These are some of the digits from MNIST. We've trained a model on some initial data set. Now we may know that some digits like 4, 7, 9 have some similar structure. If you notice the heat map or the confusion matrix, 7 and so 7, when actual digit is 4, it can be predicted to be 7 quite often, right? And 9 also somewhat. So what we're saying is that some of these digits, because of the similarity in structure, they may get labeled, they may get confused, or they may get labeled wrongly. So it is quite possible that we may want to not, when we want to label additional samples, we may want to get more of 4, 7s and 9s, because that's where a lot more ambiguity exists rather than between, let's say, 0 and 5 or some other pairs of characters, digits. Not necessarily, this is just a motivating example. This is not the case only for classification, but even for regression, we want to get most informative points. So let's look at some train points shown in black, some potential train points. So these are the points which we'll call as a part of the pool set, for which we can get the label, which means we know the X, we can get the Y. We don't know the Y yet. And the test point says everything else where we're testing. So in this case, I fitted a Gaussian process regressor, but you could have very well fitted a Bayesian neural network. And I'm showing the model uncertainty that I've obtained. So naturally, you'll see that at the black points, I seem to have zero uncertainty. So this is known as a noiseless model, noiseless GP regression like model. There is no uncertainty at the points, which are the train points. And the RMSE on the test set is 0.467. Now I've again got A, B, C, D as 4 points. Which of these 4 do you think you should label? Let's label 2 points. Which 2 of these would you want to label? Okay, which of you want to label A and D? Who wants to label B and C? No one. So I think everyone has got the gist. If you were to label B and C, you notice that previously the RMSE was 0.467. Now the RMSE is 0.409. So it's not changed much. But if I go to the original model and now add A and D, the RMSE is 0.266, and you can see the functional form has improved significantly. Why is it a case that adding A and D was more useful? We seem to have a lot more uncertainty at A. You can notice the uncertainty by the width of the confidence band that you have, uncertainty band that you have. And similarly at D also you have a lot of uncertainty, whereas for B and C you don't have a lot of uncertainty. Any particular reason why you may not have a lot of uncertainty at B and C? They change slowly. There is a change in slope. So the other reason, the easier reason I would say, is that they're very close to training data points. At training data points, we have said that assuming the noiseless model, there is zero uncertainty. So therefore, the uncertainty also has to be a smoothish function, right? So therefore, there is very low uncertainty at B and C. So for points which already have very low uncertainty, even if you label them, there is not much to gain. But if you were to label points A and D, which had a lot of uncertainty, by labeling them, the model will improve quite significantly. So thus the main aim in active learning, this is picked up from a very thorough review paper from Burst et al. You have initial label training data set, typically not a huge data set. You learn a model on that. You have a large unlabeled data set called the pool. You use a model to make predictions on the pool. When you make predictions on that pool, you will have you'll make, let's say for a classification task, you will predict the probability of each of the class, right? Then based on those probabilities that you have obtained, you can calculate some function of those probabilities, such as entropy, right? Which gives you some notion of the uncertainty that your model has. Based on that, you will select a small subset of that to query, which you give to the human annotator or to a sensor or to whatever, to get the corresponding y's. So we had the x, we chose a subset x pool from U, we obtained the labels, and thus we have a xy pair. We send that xy pair to the label training data set, and we keep on repeating till the model achieves desired accuracy, right? So we remove the points from the pool once we have added them to the train. So both operations typically happen together. Add points from pool to training data set and delete the corresponding points from the pool set. Any question in this? So this brings us to the next question, that how do we select which set of points to label, right? Let's consider the case of classification we were discussing. So let's consider a trained model on MNIST examples. We have 3 different samples I'm presenting, and this is my model's prediction for for these three different images. Let's look at model's prediction for the image 2. It predicts the highest probability of class 1, and that probability is 0.24, and it predicts the second highest probability of class 3, which is 0.22. Right? So now, do you think the model is uncertain over this example or not? And how would you consider that? How would you make such a conclusion? So you just need to look at all the bars in this figure to make some sense of what you may find useful to quantify uncertainty. And these are typically heuristics. So you don't have to think of something very sophisticated. Yes, Bhavesh. Okay. Excellent. The highest probability value which is being predicted is also a low value, right? Which means that the most probable class also has a low probability. Let's consider the other examples. So in this case, the max probability is 0.24. For this one, the max probability is 0.31. And for this one, the max probability is 0.29. So we can consider one such function, acquisition, we call it an acquisition function. So based on that, out of these three images, if the acquisition function is looking at the maximum probability, we will then choose the first image, right? Because the maximum probability is the lowest for this particular example. Right? So typically people end up maximizing the acquisition function. So therefore they may do 1 minus the maximum probability and maximize that function over all the examples X in the pool. Okay, so that is one such acquisition function which is looking at maximizing 1 minus max proba over the samples in the pools. What else could we do? Okay. 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 So it seems that from this example, the model is confused between class 1 and class 3 because the difference between the max probability label and the second highest probability label is very small. So therefore we can consider that this example is very likely to be confused by the model. Therefore this becomes a good candidate. So we can look at the difference between max proba and second max proba and do 1 minus the difference and maximize that. That becomes your acquisition function. For this example, 0.31 minus 0.4, it's a large number, comparatively large number, and for this one, 0.29 minus 0.16, again 0.13. So therefore from this particular acquisition also, it seems that out of these three images, 2 will be picked up. Okay, someone else needs to now tell some other acquisition function. Yes, sir. You can use entropy, which is the first acquisition function you can potentially think of. So entropy, if you have a very peaky distribution, it means you have a lot of clarity on what the sample is. The model has a lot of clarity on what that particular sample could be. If it is very diffused, the model is highly confused. So that particular example could be very well useful to be added to the training data set. Any other acquisition? I had these three in mind.
Can we consider say if it is 1, that is event A, and if it is 3, it is event B for the original number 2. Can you say that probability of 1 or 2, 1 or 3 can be minimized?
So in this case, it's 1 and 3. But for this case, the most probable and second probable classes are changing.
So maybe we can first find out which are the 2
Okay. So what Ritik says is that we do the addition of the max proba and the second max proba, and that should also be a very small number if it's a very confusing image. So if we add these two numbers, the max proba and the second max proba, it comes out to 0.46. In this case, 0.31 plus 0.14, 0.45. In this case, it's 0.29 plus 0.16.45. All of the numbers in this case actually are quite similar. But as these are heuristics, you can pick up and choose. But the most commonly used ones are entropy and then the margin one. The margin is the one where you look at the max minus the second max, and the least confident one is the probability of the max of the most likely class. Right? So therefore, I am representing these three numbers. 0.24 corresponding to the most likely class probability, margin sampling corresponding to max minus second max, and entropy corresponding to the entropy over this probability space distribution. So what I'm now doing is, over time, I'm picking up according to these three different strategies: least confident, margin sampling, entropy, and random sampling also. So random sampling is what you would typically do if you didn't have active learning. You could have randomly picked up a point from the pool, labeled it. But we said that all points are not useful. Therefore, we would hope that strategically acquiring points would be more useful than randomly acquiring points. So if we run this, we can see that the random sampling, all of them are improving over time, but the random sampling one is improving quite slowly, whereas the margin sampling one is improving quite quickly. And if you were to plot all of them together, we can see that the margin sampling one is significantly better than the others. Right? There's an important caveat: whenever we run random sampling, we typically run it over different random seeds, and then we report the mean and the standard deviation, because we could have just got lucky or very unlucky for one random seed. So therefore, you have to pick up different random seeds. Any question till now? Similarly, for regression, we can do. We typically pick up, we have an acquisition called the uncertainty sample.
And in random sampling, do we also pick up the points that were predicted correctly, or
So in random sampling, we have, so these acquisitions typically don't, so that these acquisitions just help you decide based on the input features and the model's prediction. After that, you get the label and put it into the training data set. Typically, people don't see whether it was correctly predicted earlier or not. But that's a good point. So he's saying that was the model correct in classification of this point or not. So you could perhaps factor that into the acquisition. Rather than just looking at the uncertainty, you could also okay, we can't do that. We can't do that because we'll have to get the correct label of the point, and that is what we're trying to avoid. We can't do that. Yes. What if we have some anomalous data? Any answers? The anomalous data is the one where the model is likely to be very confused over. And if you add that, the model will it's likely to become worse, right? So typically in practice, you want to not add those kind of points. You could either assume you have removed them beforehand, or your model is robust enough that it can handle such out of distribution points. But that's typically something to consider, right? We're also looking into, so currently if you notice, all of the things we're trying to consider, we are trying to now add the points where the model may be the most confused, right? So we are trying to add some diversity to the model. But could we also do the opposite? Could we also add some representative points, right? Let's say the centroids. Why might that be a good idea? Because those are the most representative points, right? You want the model to be performing well in the average case. But diversity helps take care of the very difficult points of the outliers, or the not necessarily outliers, but the points over which the model is highly confused on. But at the same point, you may also want to consider some representative points. So therefore, people can also come up with acquisitions which are a combination of representativeness and diversity. Thus far, whatever we have considered will go in diversity. We can do the same thing over regression models. In this case, we are looking at the GP model. And here the notion of the acquisition that we're using is just entropy or just the standard deviation. So for a normal distribution, the entropy turns out to be proportional to the sigma, right? As there is a formula for that. And let's see, if you were to add points by uncertainty sampling, add the points where the model is the most uncertain versus randomly add points. So let's do this one iteration at a time. So it seems so, okay, we are also showing the next sample to query. In this case, the next sample to be queried at the first iteration is this one, red one, because that's where the model is most uncertain, whereas in random it can pick up from anything. Now after we added that point, the next most uncertain point becomes close to minus 0.6. That's where the highest uncertainty is. And on the left hand side, we're looking at the RMSEs. Right, so you notice that through this method, we'll end up picking up points which are maximally far from the current set of training points. Right, so it's just a space filling design that way. We keep repeating this over a few iterations. And you'll see that the uncertainty sampling one, in terms of the fit, is better. In terms of the RMSE is also better. So because if you notice here, there is a lot of uncertainty still, and you notice here the function form is wrong, the mean prediction is wrong, as well as the uncertainty is huge, and it had unnecessarily added a lot of points over here. Whereas if you notice for uncertainty sampling, it seems more or less very uniformly distributed points. It ends up adding points which are maximally far from each other. There are some variations to this. We will not discuss those today. So thus far we had looked at models which already give you uncertainty. In case of classification, you already get the predicted probability vector. Through that you can calculate certain uncertainty acquisition, certain acquisition functions. For regression, we got that through using a GP or an equivalent Bayesian neural network. There are other methods of getting uncertainty which involve creating a committee of learners, creating an ensemble. So the committee could be, let's say, a same model with different hyperparameters. So let's say you have decision tree 1 with max depth equal to 5, another decision tree max depth equal to 10, another decision tree with max depth equal to 20. So you can create a committee of 3 decision trees, or a committee of same model but different segments of the data. So which is like bootstrapping. You're constructing different let's say KNN models over using the same K but over different segments of the data, or the different models with the same data set. You can have KNN, SVM, neural network, etc., and then you combine their predictions. So therefore, you can look at the disagreement amongst the different models as a notion of uncertainty. So I'll not go into a lot of details for this, and I'd rather jump into the code. Any questions till now? So this particular tutorial from Bursettles is a very accessible tutorial. It should not take you a long time to at least do a first skim read through this. There are a lot of important problems mentioned here. So we've looked at some query strategy frameworks. We also look into various problem statements. So when you're doing active learning for structured outputs, or you're looking for classification or for clustering, active learning for clustering. So the other important things is practical considerations. For example, currently we could, so do you want to label one point at a time or a batch of points at a time? For models like neural networks, you definitely want to label a batch, so as to make the training more efficient. The other problem is of noisy oracles. So sometimes we get the correct ground truth, but many times we may not be able to get the correct ground truth. Can someone tell me an example of that? There could be human error. As an example, let's say that I gave crowds, I gave a few set of images to all of you to label, and I wanted to do majority vote. But let's say half of you got it correct, some of you got it wrong, etc. So in that case, the oracle itself is noisy. Right? I do not get the correct label. Variable labeling cost, what do you think this might mean? Okay. Okay. Yes, so some images, some inputs can be differently, it could be harder or easier to label. Similarly, in the case of when we're collecting participant data, so maybe young participants and very old participants data is much expensive to collect, because you'll have to somehow be able to get access to them, get them to the clinic, get their data. They may also have a lot more difficulty in giving the data compared to a healthy young individual. Multitask active learning. So let's say that you want to do active learning, but not just for classification. You want to do active learning for classification, segmentation, something else. So do you want to add points from the pool to the training dataset on a per task basis? No, right? That doesn't make sense. Why do you want to add that? You would rather want to pick up points which are useful across different kinds of classes. You have other important considerations, changing model classes and stopping criteria. When should you stop? And then how some of the things in active learning are related to semi-supervised reinforcement, somewhat, etc. So it's a very nice small 50-page article that you can read. Now let's go into some code. I will be reusing the code which I had used in the previous class, which is the CIFAR-10 dataset. So till this point, I think all of you would remember what we studied. We downloaded the CIFAR-10 dataset, which is 60,000 images of size 32 cross 32, 3. We have 10 classes: airplane, automobile, bird, cat, deer, dog, frog, horse, ship, truck. He's showing you some of these images. Because these are 32 cross 3, so the resolution is expected to be very poor. I'm dividing the train test pool splits. So first, 1,000 points are in training, 20,000 points are testing, 39,000 points go in the pool set. I use a ResNet classifier. I can actually keep running. So I'm using the ResNet classifier, which I'd shown in the previous class. And this is the summary of the ResNet model. So it's total. So you can view it as a scrollable element, and you can see that the total number of parameters is 11,444,300 parameters. So it's a lot of parameters. We had already shown you the get accuracy predict functions previously. So the untrained model gives us an accuracy of 7% on the train, about 7% on the pool, and about 7% on the test. So this would be a good exercise for all of you to figure out why the automobile class is predicted so significantly in an untrained model, and airplane is not predicted at all. Right? So firstly, you'll have to go from the probability space back to the logit space, and then that is explaining you the predictions you're getting from the model. But you can investigate it a bit and figure out why this is happening. Ideally, you'd not want this, right? Ideally, you'd want a more uniform distribution across the different classes. These numbers are poor, which is good for us, because if these numbers were itself good, it would indicate either a lot of imbalance or something, some bug. I'd also shown the code last time for visualizing the embeddings, and I'd showed how the embeddings will improve once the model has been trained sufficiently or over a sufficiently large network. We can show the model training over the training data set, and once we've trained it, we can look at the model's prediction over the training. Over the training set is 100% as expected. Over the pool set is 35%. We have not yet used the pool set. Over the test set is about 35.6. So it's clearly improved.
Sir, if pool, we said that pool set is usually unlabeled,
Pool set is unlabeled.
but here we are finding, I read that somebody noted that pool set accuracy. So if we don't have labeling, then how can we?
Okay, so Ritik asks, A very good question. This is the difference between production settings and an academic setting. So in an academic setting, we will assume, so we took the entire data set, but we'll play honest researchers. I will not see the labels of pool. Right? Until unless I'm labeling those points, I will not see the labels. Imagine if you had to do this in the production setting, you will actually have to reach out to people and ask them for the labels or get a human annotator to do that. But we are not going to do that because our focus is not getting actual annotation, it's to show the efficacy of the algorithm. Other questions? So we can see that the model embeddings over the training data set has significantly improved as a consequence of being able to fit quite nicely. Over the test points, it's still quite hazy, and that explains why the accuracy is poor. Yes. I have not used a validation set to comment on whether it's overfitting or not. I have not even looked at the test performance over iterations to comment on it yet. And then when we train the model on both the train plus the pool data, we saw this in the previous lecture also. The embeddings over the test set have significantly improved now. It's still not perfect, they've significantly improved. The accuracy over the train set is now 98%, over the pool is 98%, over the test is about 61%, right? So let's look at the numbers again. Untrained model, what accuracy? Anyone remembers? 7%. Only trained data, model accuracy, 35, 36. And train plus the pool set is the larger data set, it's about 39,000 points. So in total 40,000 training points, the test set accuracy becomes 61%. Right. Why have I done this experiment of computing the accuracy over the train plus the pool set? Can anyone suggest why I've done that? So that's likely the highest accuracy we'll be able to achieve using this data set, assuming this fixed test set, right? And we are assuming that as we're adding points, the accuracy should only improve. So in that setup, using both the train and the pool together is likely the upper bound on performance on the test set. So therefore, it's important to do these calculations, and we can do them in the academic setting again, or in this kind of an evaluation setting. In real world scenario, we will not be able to do this. So if this gap was not very huge, what do you think is the research problem at hand? Or if this gap is not huge, should we bother with active learning? No, right? Which means that if you just trained on train, that is giving you comparable accuracy with if you were to train with the entire train plus pool, which means you're not adding any new information from the pool. The model will not improve. So therefore, this is an important study. This gap is important to first establish. Next, I'll show the active learning loop. I will also be requiring a function called set difference 1D. So this takes two torch tensors A and B, and it computes the difference in between them in the set notation. So A minus B. So if I do A 1, 2, 3, 4, 5 and B is 1, 3, 5, then the set difference between A and B is 2 and 4. Where might I be using this function in active learning? So we have to figure out some chosen points. We add them to the training set and we remove them from the pool set. So that is where we might need such a function when we're trying to remove something from the pool set. I've created a simple active learning loop. There are far better methods to do this using object-oriented programming, using more modular functionality, etc. But I just wanted to show a quick and dirty implementation. I'll have an active learning loop which takes as input a model, a query strategy. The query strategy, one such query strategy is random. So I randomly choose points to label, number of active learning iterations. So in each iteration, I want to pick up query size number of points. In each active learning iteration, I want to pick up query size number of points, number of epochs fine tune. Whenever I add a query size number of points from the pool, get the labels, add them to train, how many epochs do I want to fine tune over the entire data. Typically, we will want this to be a small number, not a very big number. Index of the training data set, index of the pool data set, index of the test data set. And the query size X and Y device, I'm running this on random seed and verbosity checking whether I want to print things or not. So I am taking some copies of train index, pool index just for safety purposes so that I don't end up modifying these in place, because these are globals currently. Train index, pool index are globals. I don't want to be modifying them. Before I do any testing, I get the initial accuracy of the model before training, and I put that in a variable test accuracy with, for the 0th iteration, that is my accuracy, init accuracy. This is the main loop. I want to run my active learning loop for num AL iterations. I first put the model in eval mode. Why do I do that? Sorry? We'll be only doing testing, we'll be only looking at the testing phase of it, right? So does everyone here know the difference between model.eval and torch.nograd? When to use which? When we don't want the computational graph, we want to use with torch.nograd, and model.eval, that we want to use the model for the evaluation purposes and not for training purposes. But why do we need this? Yes, excellent. So there are some particular layers which behave differently in train mode and the test mode or in the eval mode, such as dropout, such as batch norm, etc. So therefore, you have to be a little careful with the mode that you're giving. At the present moment, we don't need, the model has some dropout, but I don't need the dropout now. So therefore, I'll put the model in the eval mode. So this is a general structure that I've given. Query index or indices is, I'm obtaining that as a return from the query strategy, which is a function. I call this function over model, pool index, train index, random seed, query size, X, Y, and the device. The reason I've done this is that I just need to now define these different query strategy functions. And this, my active learning loop is independent of that. Once I obtain these query indices, I add them to my training data set by concatenating with the original training data set. I index with the query indices, and I remove them from the pool indices by calling set difference 1D. So this is where we'll use the set difference 1D model. After that, I'll call the train function over my model, over the X train index, which has been updated, and the Y train index, which has been updated, and everything else is the same. After I've trained the model over the new data set or fine tune the model over the new data set for some num epochs fine tune, I store my result of test accuracies for iteration plus 1 in this variable, and then I return model train index, etc., etc. So whenever we're writing such functions, it's important to first be able to write the random sampling well, random query well. And random sampling, we don't have much to do. We as such don't need the model. So this is something which you should very nicely appreciate from VS Code. It is highlighting the variables which are not getting used. Random sampling, does it need a model? No. It randomly picks up from the pool index. It doesn't need the train index. It is needing the random seed because I'm setting the random seed. Because when I make multiple runs of random sampling, I want to try with different random seeds. Query size it doesn't need X and Y, it needs, in this case, it's not using the device. So I set the random seed, I randomly pick up from the pool index a query size number of indices and I return them. So then when I'm running this active learning loop, I'm running for a query size of 20, which means that for each active learning iterations, I'll label 20 points, 20 images. And I'm running my active learning loop for 50 iterations. what is the total number of images I'll add at the end of this cycle? 15 to 20,000. I am copying the model which I had used, which I had trained only on the training data set, and I'll be reusing that. So all I now need to do is to call this AL loop with the correct model, which is in this case just the deep copied model of the only trained model, with the acquisition strategy or with the query strategy, which is random sampling, which is a function, and various arguments like number of AL iterations, the number of epochs you want to fine tune over, training index, spool index, etc. If you run this for 50 iterations, you can see that the accuracy improves over the number of iterations. This is expected. There are some dips. This could be some spurious data points being added, or this could also be a bug. So I'm happy that I still have to check, but in the previous class, Satyam pointed out there was some bug in reshaping in the coordinate network, and he's mentioned that on the YouTube. We still have to check that, but you are more than welcome to check these. And if you're very confident, you can also directly make a PR to the class repo. There could be a bug here, or this could just be the randomness at play, right? But overall, you see that over the number of iterations, the accuracy is improving over the iterations. So typically you want to be running such experiments over multiple random seeds. So therefore you will have I'll put a for loop for random seed in range 5, and I'll have the same hyperparameter query size, the number of active learning iterations, and I'll run this over the different random seeds. I'll look at the mean and the standard deviation of the prediction of the accuracies, and I'll plot it with respect to the only train and train plus spool. Okay, as you may notice, the accuracy of the model, which is now using active learning with random sampling, is improving improving quite significantly over the only train. There is this dip at the beginning. I yet don't have an explanation for this. Probably a bug or it's random at play. But we saw this for the other acquisition functions also. So we'll see whether this is a bug or not. Okay, so this was a simple strategy. The next strategy we'll be looking into is just entropy. So entropy, we will be setting the random seed. We will be using torch.nograd. We will be running the model over the X pool. We'll get the logits, convert the logits to probabilities, or we could directly use torch's log softmax function rather than converting to probabilities and then using the softmax. Either of them will give you the right answer. I would rather prefer that we use log softmax rather than softmax. But you get the probabilities. You can calculate the entropy to be minus p log p summed over the classes, right? And then you sort the entropy that you get, and you pick up the indices corresponding to in the descending order, and then you pick up the indices corresponding to the top query size number of indices, right? So it's a simple function. Calculate the logits, get the probabilities, get the entropy, sort it in descending, pick up the top k or top query size. We again initialize the model as the deep copy of the model only trained model, and then this called the active learning loop. So because the code is modular in nature, you don't need to, okay, there seems to be some lag. Okay, this is where we were. We looked at how random sampling is doing better than if you were to use only train, but we are still quite far from train plus pool. We also looked into the function for entropy sampling and the calling of the active learning loop over the entropy sampling method. And this is the accuracy that you get when you're also using entropy sampling. So it's not, in this case, it's coming out to be comparable or worse than random. So you should not be very surprised when some sophisticated algorithm is getting beaten down by random, because random is a very good baseline for a lot of problems. This could also be a bug, but in practice, it's not very easy to defeat random. You'll have to have a hard enough problem where the strategically querying is adding some value. The next acquisition is margin sampling. You, similar to the previous one, compute the logits, compute the probabilities. The margin is the difference between the highest and the second highest probability value. Okay, thank you. So you figure out the difference between the highest and the second highest probability vector for each pool example. So this is important, over which dimension you are computing these computing these things, and then you pick up the top top queries. Okay, the next one is something which you might not have easily thought. I'm calling, so this is called diversity sampling. So what we do here is that we're looking at the model's featureizer. If you remember, the model had two components, the featureizer and then the classifier. So the featureizer, for each input x, it will give you a feature vector of the featureizer length, whatever feature dimension we had thought. In this case, for our case, because we're using ResNet as the featureizer, the length comes out to be 512 length vector, right? So for each point in the pool set, we compute a feature vector of size 512. We do the same thing for each point in the trained data set. And then we compute the pairwise distances between each point in the pool and each point in the train over the features. So what you want to do is you want to pick up the points which are very far, so pick up the points from the pool which are very far in the feature space from the feature space of the training points. Right? So let me repeat that. You compute the featureization for the pool and the train sets. Then you want to pick up the point from the pool which is maximally far from any point in the training data set. So there are quite a lot of variations to how you say maximally far, very far, close. So are you looking at the nearest point from the train? Are you looking at the farthest point from the train? Are you looking at the centroid of the train? All of these topics we also discussed when we are looking into hierarchical clustering. So all of those variations can exist. The next one is perhaps the most, so we can also look at this very nice article called Overview of Active Learning for Deep Learning. So a lot of the content we're looking at today can be found out very nicely summarized in this article, including the diversity sampling one, which we just discussed. So this idea is diversity sampling one. The next idea is from a very well cited paper called Deep Bayesian Active Learning with Image Data. So here they propose an acquisition function which is known as BALD. So I think it stands for Bayesian, what does BALD stand for? Bayesian Active Learning with Disagreement. To explain this, let's look at, to explain this, let's look at two kinds of models. So we'll be using methods such as MC dropout for this. So let's have MC dropout iteration. And first let's have probability of 0, probability of 1, okay. This is the output that you're getting from the MC dropout iterations for model 1, right? Similarly, we have model 2. Okay, so this is the output that you're getting from, let's see, should we calling it 2 points, sorry, pool point A, pool point B. You have 2 points from the pool set. For the first one, you get 0.5, 0.5, 0.5, 0.5 for all the 4 MC iterations. For the others, you get 0, 1, 0, 1, 1, 0, 0, 1, 1, 0, right? Which of these points do you think is more worthy of adding and why? Sorry? Pool A should be added? No, no, these are 2 different points. So MC dropout, is done over an input X for 4 iterations. That input X could be A or it could be B. When it is A, you get 0.5, 0.5, 0.5, 0.5. When it is B, you get 0, 1, 0, 1. Which of them of A or B should we be adding? B. How many say B? Okay, Ayush, why should we be adding B?
Because my model is very certain it's class A or B and it's looking very different.
Okay. What kind of uncertainty is higher in pool B point? Epistemic, aleatoric, which one? Model is more uncertain in pool B point. Therefore, it is exhibiting higher epistemic. Yes.
So you can kind of visualize that point B is somewhere near the decision boundary.
Mhm.
Change the parameters a bit, so then it's getting classified completely differently. It's
Yeah.
not an outlier, so then it's to be considered.
Yeah. Yeah, you could think of it from that perspective, or the perspective that the model itself is highly uncertain about this. The previous case, this could also be near the decision boundary, but the model is very, very sure it's 0.5. Right? Here it's flipping the labels. Right? So therefore, poll point B is exhibiting high amount of epistemic uncertainty. Therefore, it should be favored over pool point A. Right? So for such kinds of models, what we'll do is we'll firstly calculate the expectations over the probability. Right? So let's calculate expected probabilities. Expected probabilities are 0.5, 0.5, 0.5, 0.5. Entropy of expected probability. So first you find out expected probability, so this vector, and then you calculate the entropy. Right? So that will be a single number. That will turn out to be 1. The entropy for these will also be 1, right? So then there has to be some different way of quantifying that pool B is harder. So therefore, we'll first do entropy of P. Right? We'll calculate the entropy over P for each of these points. So for iteration 1, 2, 3, and 4. So I should ideally not be doing it here. I can actually do it here. Entropy for a point. Entropy for the first point for pool A is 1, 1, 1, and 1. Right? Entropy for the first MCI iteration point from pool B is 0. Entropy here is 0, here is 0, here is 0. Right? So if you now calculate you've calculated the entropy for each of the point. If you calculate the expectation of the entropies, if you calculate the expected entropy, that will turn out to be 1 for the pool A point, and that will turn out to be 0. Sorry, yeah, 1. Right? Whereas the entropy over the expected probability values was the same for both of them, but they're differing in the expectation over the entropies, where you first calculating the entropy for each MCI iteration. Right? And now you look at the difference between these. 1 minus 1 is 0, and 1 minus 0 is 1. So this gives you a higher number. This difference is representing the amount of epistemic uncertainty that you have. In some way, it's mutual information actually. The details are not, I'll not be able to cover the details in today's lecture. You can refer to this article. The mutual information between predictions and model posterior, it turns out to be entropy of Y minus the expectation over the different MC samples over the individual probabilities, individual entropies. Right? So I suggest you think of this in a spreadsheet-like way. In a simpler formulation, you would first find out the expected probability over the samples. So you first reduce over the MC iterations to get MC dimension to get the probability vector, then calculate the entropy over it. That is the entropy of the expected probability, or the general entropy that we've been looking into. The second method is we find the entropy for each sample, each MC sample, and then you find an expectation over the MC iterations. And then you find out the difference between these two quantities. That will be your bald acquisition number. If we are to implement this in code, you can see that first we find out the probability vector. We can then find out the expectation over the probabilities, which is what I've done here. You find out the expectation of the probabilities, which is to So this is important. My dimensionality is first is number of MC passes, second dimension number of samples, third is number of classes. If I take a mean over dimension 0, I'm calculating the expectation over the MC passes. Right? So I would always suggest you write the shapes and then figure out the dimensionality over which you are reducing. And then I can calculate the entropy over the expected probabilities. So first you find out the expected probabilities, then find out their entropy. Whereas for the other case, we first find out the entropy of probabilities, which means we are looking at for each and every MC iteration. And then we find an expectation over that, over the MC samples. And then we look at the difference between these two quantities. Finally, when we use this acquisition, it turns out to be comparatively better than random. It's not significantly better, but again, this could be a bit of a configuration, but maybe a simple data set. So we'll have to look at the analysis before making any conclusion. But fortunately for us, all of the algorithms are improving over the active learning iterations. That's all I had for today's lecture. Any other question? Okay, good. Thank you.